Today we're going to take a look at section 2.2, which is titled The Derivative. And we saw this last time, but we didn't call it this. So this is the definition of derivative. The derivative of a function f at the point x equals a is defined as f prime, and we will read that as f prime of a. It equals the limit as h approaches 0 of f of a plus h minus f of a over h. This works provided that the limit exists. And if the limit exists, then we would say that f is differentiable. Hence, you can find a derivative differentiable at x equal a. And we had another name for that last time. Do you remember what we called it?
Velocity.
Called it velocity. And we had one other thing we called it too. Remember? We called it a slope of a tangent line. So all those phrases are phrases that mean the same thing. And we may encounter one more phrase, I can't remember if your book does it or not, that means the same thing. So slope of a tangent line, instantaneous velocity, or when we say velocity, and then derivative. They all mean the same thing. Okay? Got the exact same formula, limit of f of a plus h minus f of a over h as h goes to 0. And we're going to call that the derivative. There is an alternate definition of derivative as well. And a couple of you were in my office and we talked about this actually, because you said, I thought that I remembered. And I said, yeah, there's another one too. Again, another form of the derivative is given by f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. Now before I keep reading, can somebody tell me what's different? Just visually, what do you see is different with this than the last formula?
You said x instead of an a.
Yeah, x is in there instead of a. Practically speaking, the only difference is that the last definition was defined at a specific value, a, and this x is defined for any x that will work. Okay, so it's defined for any value that will work. So the domain of f is the set of x's for which the limit exists. That is, any value will work. The process of computing the derivative is called differentiation. And we will say that f is differentiable on an open interval I if it's differentiable at every point in that interval I. The only difference between these, and in practice, the way we work with them, there is no difference. But the only difference in the definitions is that first one said, all I'm talking about is this one specific point along the x-axis. Just one place. This definition is saying, well, if I can talk about it in one place, I can talk about it in lots of places. That is, I can talk about it in any place that works. So we're going to define it in general to say, anywhere it works this way. And anywhere it works, we'll say that that's the interval where it works. So that's what you're seeing happening on this definition.
So I stands for
I stands for interval, yeah. And I think it's up here, right here where it says interval I.
gotcha.
Yeah. Any interval that would work. Now, in many cases, and in most cases as we start this, it's going to work everywhere. So the interval is really going to be negative infinity to infinity. We're not going to have to worry about it. But as we continue along, there will be some problems where we have some denominators, so it's not going to work if the denominator equals 0, things like that. So there are going to be some places where we have to leave out values where they actually work. But the process of actually calculating it will be the same no matter what. All right, so let's take a look at an example. This says that we're going to compute the derivative f prime, and we're going to do it for a function x cubed plus 2x plus 1. So what I'm going to do this time is, because I didn't do this particular direction last time, is I'm going to do it with that in general f of x notation. That is, I'm going to do it with this definition right here. Okay, the one that has the x's still in it. It really doesn't make any difference what I use. I just want to show you that in fact it will still work and look very much the same. So we're going to find f prime of x. It's going to be the limit as h approaches 0 of f of x plus h minus f of x over h. And this is what we're going to do. So this is the limit as h approaches 0. And just like last time, this notation, f of x plus h, that's college algebra notation, or potentially something called math analysis if you did it in high school. You would have potentially encountered it somewhere in an Algebra 2 or Algebra 3 pre-calculus kind of course. Okay, so this is not a calculus notation, but it's used in calculus quite frequently. F of x plus h means taking the function f of x, and everywhere it has x, I replace the x with x plus h. So I'm going to have x plus h cubed plus 2 times x plus h plus 1. All of this came from here. That is the f of x plus h. Then I'm going to subtract f of x. Well, f of x is the original function that I was given. That's x cubed plus 2x plus 1. And I'm supposed to divide all of that by h. Does everybody see where all the pieces came from? So if you lose one of these pieces, things are going to get messy and kind of blow up in your face a little bit. All right, so the part that's highlighted in blue right now is the part that needs some simplification because you see something that's cubed. And don't let yourself go along the trail that says, I can just cube each piece. That's not an algebra property. Okay, you can't just sort of distribute the cubed. That's inappropriate. So in order to deal with the fact that that is cubed, you actually have to figure out what in the world that would look like if you wrote it all out. So they've got x plus h times x plus h times x plus h minus, I'm sorry, not minus, plus 2x plus 2 plus 1, and then minus, and I'm going to keep this in parentheses or in a bracket, and the reason I am is simply because everything in this second bracket, all of it reduces with something beforehand. So I'm not going to distribute the negative. Yes?
On your second one,
Uh-huh.
on the x plus h.
Oh, it's x plus h.
That's what.
I was like thinking, where in the world? There's my h missing. Thank you. Yeah. I probably made the stroke on my pen and it probably just didn't register from the screen. But yes, thank you for that. We've got that fixed. All right, so parts of this can even simplify before even writing anything any further. For example, you see that 2x here and this 2x here? This one's positive 2x, and this one is minus positive 2x, so those aren't going to need to be in there anymore. There's also a 1 here. This is positive 1, and this is minus a positive 1, so those are going to reduce as well. So we don't actually have to keep writing them into the next step if you don't want to. Now, over on a scratch sheet of paper, and I'll do it on my screen, but I want you to do it over on a scratch sheet of paper, let's actually figure out what is x plus h times x plus h times x plus h, okay, without rewriting it inside of our problem itself. Let's just simplify that part of it. So if I have x plus h times x plus h times x plus h, the way that we handle that, if you'll remember, is we take two of them and we multiply. Okay, so if I multiply two of them together, I will get x squared plus 2xh plus h squared. And I get that by taking x times x, foiling is an acronym that you often hear used, so that gives me an x squared. The inside terms is h times x, and the outside terms is x times h. They're the same. So that's the 2xh in the middle. And then the last terms is h squared. And then after that, I'm going to multiply each of those, that is the x squared, the 2xh, and the h squared, times x and times h. So I'm going to get, let me move this up a little bit, x cubed plus 2x squared h plus xh squared. That's taking the x squared and the 2xh and the h squared and multiplying each of them by the x. And then I'm going to multiply each of them by h. So that's going to give me x squared h plus 2x h squared and h cubed. So some of these are going to combine. Obviously, x cubed doesn't combine with anything. So I've taken care of that one. What is going to combine? What's going to combine with the 2x squared h? Yeah, this one and this one, right? So those two combine to give me what? 3x squared h. The next two also combine, right? Xh squared and 2xh squared. So that gives me 3xh squared. And then the last one is h cubed. So all of those pieces are going to go right up here. That's the simplification of that part that had the three things multiplied. Okay, now I need more space on the screen, so I'm going to just erase what I've done down here, the scratch work in purple. Does everybody have it before I erase it? All right. So the part there in red then we just found out is x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I've still got this h here left, this 2h. So I've got plus a 2h, and I've got minus an x cubed that's there at the end. But like I told you, everything that was subtracted off at the end reduces, so that h cubed also does, right? Sorry, not h, x cubed also does. This x cubed and this x cubed add to 0. That's really important because we talked about this last time. Everything in the numerator has to have an h in it when I'm done with the simplifying. Otherwise, that h in the denominator, which is causing my problem, right? It's the one causing the problem. It's what's not allowing me to put in 0 in for h everywhere right now. I need that h in that denominator to go away. Otherwise, I can't plug in h equal to 0. So everything in the numerator has an h in it now, which is what my goal was. So I can factor an h out of the numerator. So this is now 3x squared plus 3xh and plus h squared plus 2 over h. Did I get all of that right? Are all my pieces there? I think they're all there. Looks good. And I do this so that I'm able to reduce the h here. Now I can plug in 0 for all my h's, and when I do that, what happens? What do I get?
A whole lot of zeros, 2 basically.
Yeah, I get 2 zeros and 2 things remain, right? So I've got 3x squared. 3x times 0, that's 0. 0 squared, and 2. So what remains from this?
2. 3x squared plus 2.
The 3x squared and then the 2. Okay? So back up here, I'm going to write my answer up here at the top since that's where I've got space still. The 3x squared is still there, and the 2 is still there. So my derivative, f prime of x, is 3x squared plus 2. Some of you were looking at that and said, I knew that to begin with. I know, it's okay. Some of you don't. But you will in 2.3, okay? All right, so this is the notation.
It's going to feel like Christmas.
What's happened?
when we finally do that.
Okay, let's do an interesting one. This one's got a square root in it. So even those of you who've done calculus before may not have a real quick way to tell me what this is. All right, there is other methods, and we will encounter them this semester, but not in 2.3. So in 2.3, when you learn the shortcut for doing problem number 1, it's still not going to tell you how to do problem number 2. Okay, there's another method for that one. But we're going to do this the same way, all right? So we're going to do f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. And while you may not be super fond of the square root that's involved here, the algebra for simplifying this isn't actually quite as messy, to be honest, as the algebra on the last one because of that cubing power, which is kind of messy. All right, so this is going to be then the limit as h goes to 0 of the square root of 4 times x plus h minus 2 minus the square root of 4x minus 2 over h. So this piece and this piece are the same. Remember, all I have to do to get the f of x plus h piece is replace the x with x plus h. So I'm going to have a square root in 2 different pieces, and they don't match because one of them has an h in it and the other one doesn't. So there's not going to be a way to combine these 2 square roots yet because one of them has that h and the other one does not. Now, the fact that one of them has the square root in it, or has the h in it and the other one does not, somehow that h that's underneath that square root's got to come out, or I'm not going to be able to simplify with the h in the denominator. Agreed? Now, you did a homework problem that's going to look like this already, and you did a problem on your test, and most of you did a very good job of doing the problem on your test. You had square roots, and things did not allow you to plug in the number you wanted to. What did you have to do to work with those square roots? Conjugates. So we're going to use conjugates here as well. Now, I'm going to do one simplification step right here before I do the conjugate, just because it looks a little bit messy. Whoops. It looks a little bit messy with the parentheses underneath that radical. So we're going to write this as 4x plus 4h minus 2, all underneath the radical. Be careful with your radicals so that I can tell what's under and what's not. And then the 4x minus 2 on the other one. All right then, so what in the world is my conjugate going to be?
The same thing as plus 4x.
Right, same thing. With a plus sign between my two radicals, right? And this time I actually have two radicals. You don't always have to have two radicals to have a conjugate involved, but this one does. And if you do that to the numerator, which is where we actually need it to happen, you of course also have to do it to the denominator. Now, why in the world did we do that in the numerator? What was the purpose in that? Why do we multiply by conjugates?
To get rid of the square root.
Yeah, it really gets rid of the square roots. So what actually ends up happening is that the first two terms multiplied are identical, so the square root goes away. So I have 4x plus 4h minus 2. The inside term with the square root of 4x minus 2 times the square root of 4x plus 4h minus 2, this piece ends up being the same thing as the outside term. They're identical except different signs. One of them is positive, one of them is negative. That's a really good thing, because if one of them is positive and one of them is negative, they cancel each other out. So I don't have that square root involved anymore. And then I have my last two terms. One's negative and one's positive, so this will be subtraction. But then I've got the 4x plus 2, minus 2 underneath the radical on both of them. So again, the square roots cancel out. So I have 4x minus 2 here. I have an h in the denominator, and I have this ugly, weird square root thing going on. We don't need to distribute that h through. That is an unhelpful process. So we're going to leave that h on the outside. So it looks like this. The numerator, some things simplify, so tell me something that simplifies in that numerator.
4x's.
The 4x's, yes they do. What else?
2's.
The minus 2's, they simplify. So what is left in my numerator? 4h. So I have 4h on top, I have h on bottom, and I have these weird square roots still on bottom. So my 4h on top and my h on bottom reduce to what? 4 on top. Some of you had some problems remembering that piece in your test. So 4 on top. This allows me to actually have the 0 put in for the h. Notice what happens if I put 0 in for the h right here in this little square root. What's going to happen? I get 4x minus 2, which is the same thing the other one is, right? They're going to match. Once 0 is plugged in for h, the two square roots in the denominator match. Do you guys see that okay? That's a really helpful piece of information because once they match, they can be combined. They're now both 4x minus 2. So what happens when I add the square root of 4x minus 2 plus the square root of 4x minus 2? I get 2 of them, exactly. So I don't get the square roots to go away, right? I'm just adding. But I do get 2 of them. So what that means is I've got my derivative. I'm sorry, I've moved back up to the top now because I've run out of space. I need to write smaller, I think.
Is it supposed to be an x after 4?
Oh, did I leave it off? Oh, yes. You betcha. Thank you. All right, so right now in the numerator, or right now at the very top of my screen, I've got 4 over 2 square root of 4x minus 2, and I can simplify the 2 and the 4, right? So this will give me a 2 on top. So my final answer, so to speak, is 2 over the square root of 4x minus 2. And we won't find a shorter way to do that until either Thursday or maybe even next Tuesday.
But chain rule or is it power rule?
It's chain rule.
Chain rule?
Yep. There's a power rule involved with there too, but yes.
Is
Mhm.
it required that we simplify anymore? Because like you can simplify now the square root of 4x minus 2 over 2x minus 1.
That's a really good question. So let me answer that for you, Luke. So the word you use is probably not quite the word you meant. So the question is, where's the problem stop, right? I mean, that's the question. Can I stop here? So somewhere along the way, you learned about rationalizing denominators. The difference between that and what's going on here is that when you rationalize denominators, you knew the denominators were a value. This has a variable in it, a variable of x, which means that sometimes the value for x will actually make this a whole number in the denominator. You can take a square root of it, and sometimes it won't. So there's no reason to rationalize a denominator here. The denominator having a square root in it is perfectly acceptable because it depends on what the value for x is as to whether or not it's rational or irrational anyway. So there's no reason to rationalize a denominator from this point, okay? Because you don't have a number in the denominator, you have an expression. Sound good? Okay. All right. There are other things we can use besides that f prime notation. And I don't necessarily care which one you use, but you do need to be aware of them because they are helpful in different contexts. So the first one is the one that we've been using, f prime of x. But just like we interchangeably use f of x and y, we could also use y prime instead of f prime of x. Well, depending on whether or not you use y or f will depend on which of these two in the middle, because they're really the same, right? dy over dx and df over dx. Let me talk about why this notation has some help to it, or at least some visual niceness to it. Last section we talked about derivatives, but we called them something different. We called them slopes of tangent lines. Well, when I see that dy over the dx, can you see how that looks like a slope? I've got the y over the x, and d means change in, kind of like that delta notation that you saw somewhere along the way. It has that same connotation, delta x over delta, or delta y over delta x, change in y over change in x. So these two in the middle have a very helpful sort of a slope feel to them. The one at the end kind of mixes the two notations. It's the change in x, d dx, that's what we would read that is, the change in x, for the function f of x. So it just kind of mixes the two notations. Honestly, the two that you see the most are either one of these in the middle, again used interchangeably, or one of these at the beginning, used interchangeably. So it doesn't really matter which one you see used. You're probably going to do the prime one. It's a little quicker to write. Looks very nice in terms of writing down y equals and then y prime equals. But we will see a notation for the dy dx. I can't remember if it's toward the end of the semester. I think it will be toward the end of the semester. And then for those of you going to Calc 2, you'll see it again used in there. Okay? So just for now, just be aware that they mean the same thing. They mean derivative.
So dy dx, like in my old calculus class, we basically, I don't know why now if they're all equal, but we used dy dx when we did implicit
Yep,
differentiation.
we'll use it there. We will.
But could you, it just makes it easier, I feel like.
Yeah.
Use dy dx, 'cause you gotta
You
make
can
sure.
also use y prime when you use implicit, but it's not as, it's more prone to problems.
Yeah.
We'll say it that way.
It's good to have the x and y.
Yeah.
Yeah.
Yeah, it is. Yeah, for right now, it doesn't affect anything because we're not going to be doing that yet, but we will get there, all right? All right, let's take a look at sketching some graphs. I think this is an interesting section. Some of you are probably very visually inclined. You like to see pictures. They help you. I have a brother-in-law who is a doctor, like a medical doctor, and honestly, the way that he remembers the alarm code on the house is a visual picture. He's got a keypad, and he knows where the keypads are. I mean, he knows what the numbers are, but the way he remembers it is a visual memorization of what button he pushes in what order. And so some people are very visually oriented, and some people aren't. And so you may find this section to be either more challenging or less challenging based on that information. So what we're going to be doing is we're going to be taking a graph of a function and trying to sketch a graph of the derivative. Or we could say sketching a graph of the slope. the slope graph. So the goal is to start with a function and draw a graph of the derivative. That is, it represents the slope of that first function at every point. And I'm sort of writing down a list of steps because I think that it's most helpful to not miss any of the pieces. So specifically, we're going to observe some very key points on the graph to help us do this. So the first point on the graph is to identify where slopes are 0. Now we talked about this, I know it's been like a week ago now, but we talked about this in general happening when we had a graph that did something like this, and it had a point right here. And do you remember drawing the tangent line and it looked like that? Well, if that's the tangent line, what's the slope of a line that looks like that? 0. A flat line has a slope of 0. So finding where slopes are 0 is very much, at least in most cases, equivalent to finding peaks and valleys of graphs. So if you want to sort of write yourself a little note beside that peaks and valleys, that's most of those locations. There are some other ones that have 0 slopes that are not peaks and valleys, like this one. And we saw this last time as well. We actually, in order to draw the line that is going to be the closest representation nearby that point, it's going to be a horizontal line that actually cuts through the graph. But it cuts through as close as possible. So it cuts through in this fashion. And again, the slope is 0. So when we have these flattened out places, as well as the peaks and the valleys, we have slopes of 0.
So that one's okay to cut through like that because it's pretty much impossible to make one.
Yeah, there's no way to be close that is hugging the curve on both sides without it cutting through. But it still has to cut through very close to the curve, which means it's going to be a flat line as opposed to, say, a vertical or a diagonal line. All right, the second thing we're going to do after finding where the slope is 0 is we're going to identify where the slope is either positive or negative. Now, in general, it's really nice to read a graph sort of from left to right, because that's how we read English. We start at the left and we move toward the right. So you might say, okay, from negative infinity to this place, it's doing something. And then from this location, we'll call it A, to over here to B, it's doing this. And then from B to C, it's doing this. And then from C to infinity, it's doing something else. So we may see us, and that's how I will write it, because I read the graph from left to right like I read English. So that's what we're going to do on number 2. And on number 3, I wrote this word sometimes in there. Sometimes this is necessary, and sometimes it's not. So when is the sometimes? Well, the sometimes has to do with how much information 1 and 2 give you. If you get a lot of information from 1 and 2, you usually don't need to do 3. But if 1 and 2 give you virtually no information, and I'll show you a case where that happens, and you'll be like, oh yeah, I don't have enough information to do anything, then we're going to have to do C, 3. Okay? Notice how the slope is changing. All right. So let's take a look. We've got a graph. And we're going to write down a list of features about this graph. So when you do this problem, it's going to say these directions exactly. Use the graph of f to sketch the graph of f prime. The work that you show will be the language you write down about the graph. So you are going to draw a graph, but that's going to be the answer. Okay? So the answer is going to be the graph. The work in between is going to look like a list of features about the graph. So we're kind of just going to go through this one at a time. So the first thing we're going to do is we're going to look on this graph at places where the graph appears to be changing direction or having a slope of 0 that's flat. So in this case, I'm looking like this particular point here and this one right here, which were conveniently labeled A and B for you, have places where you've got a peak and a valley, right? So what we're going to do is we're going to write this down, and we're going to write the slope is 0 at A and B. And I really want you to write the word slope. You might be just tempted to write 0 at A and B. Please write the word slope for a moment. You'll see why when I get there, okay? Write the word slope. Second thing, number 2. So I'm going to read the graph from left to right. So if I start on the very far left and I move towards the value of A, what can you tell me about those slopes?
Negatives between A and B.
Okay, but I'm going to start over here before I get there to here. So, right, if you go from the left all the way to the point A, the graph's increasing, right? But the slope is positive. So we're writing statements about slope, not about the graph increasing, decreasing. So don't use the words increase, decrease. That will be unhelpful at its height. Not helpful at all to you, okay? So we're going to use the words positive and negative referring to the slope. The slope is positive. So from negative infinity to A, the slope is positive. All right, so somebody already told me between A and B. What's happening between A and B? It is decreasing, but we want to write the slope is negative.
Okay, so those are open, not brackets, the A and B.
Correct, because the slope is actually 0 at A and at B. How about from B on? That is B to infinity. The slope is again positive. Okay, does everybody have this list of statements written down? This is plenty enough information. We don't need to do step 3, okay? We've got enough to do it from here. The next thing I want you to do is if you have another colored pen or pencil with you, grab it. If you don't, just use the pen you're using, that's fine. But it will be helpful for you looking back at this later to recognize what we're about to do. All right, everywhere you wrote the word slope, I want you to mark a line through it, and I want you to write the phrase y value. Okay, so everything you wrote down originally was statements about the slope. Agreed? All statements about the slope. Where was it 0? Where was it positive? Where was it negative? But what we need to do to answer the question is we need to draw a graph, and the graph needs to be a graph that tells us information about the slope from the previous graph. All right? Now, here's the first thing. When you draw this axis, wherever A and B originally were, they need to be roughly in the same place. And if the graph includes things before, on the negative side of the y-axis, you need to include the negative side of the y-axis. Okay, so you have to have the same sort of visual picture that the original axis had. So roughly here was A and here was B.
Unless we're not just drawing it on top of the graph.
No, please do not draw it on top of the graph because then, well, you could on your paper, but you're not going to do it on your book because then I wouldn't have the book page. So when you do this in your homework, you don't need to draw the original graph at all. Does that make sense? So you're just going to draw this particular graph. So I'm going to draw it separate because that's what you'd be turning in. All right, so the first statement said, originally, the slope is 0 at A and B. Now, written in red, it says the y value is 0 at A and B. What does it look like for a y value to be 0? It's the x-axis. So that point A and that point B are now x-intercepts because those are points where the y value is now 0. All right, so the slope was originally 0. Now the y value is 0. And we're going to read the graph from left to right. This said, originally, the first line on number 2 said that the slope was positive. Right now it says the y value is positive. What does it look like for you to have a positive y value? Above the x-axis. So before we get to the point A, that is moving from the left side of the graph until we hit A, we need to be above the y-axis. So I need to cut all the way over to the left-hand side because the original graph was also on the left-hand side. Are you guys with me on that? So the graph needs to go all the way to the left-hand side. That's above the y-axis. It was curved to start with, so drawing it curved right now sort of makes sense. Right? What is supposed to be happening between A and B?
Negative.
Yeah, the y value is negative. Well, what does a negative y value look like? It needs to be underneath the x-axis. But it still has to connect where I've already drawn my points in at A and B, which means it has to start at A and get to B and do it underneath the x-axis. So it's got to have this sort of a curve underneath the x-axis going on. What happens after the point B?
Goes back to positive.
Yeah, it's back positive, so I've got a y value positive, which means I'm above the x-axis. So this original graph over here was the graph of f. This red graph that we've just drawn is the graph of f prime. It's a sketch, okay? So if yours looks, like taller and skinnier than somebody else's, that's not a big deal. This is a sketch. The image will still have the basic overall image. All right, ready to take a look at another one?
Yeah.
All right. Example 4. This is the graph of f. Now this one purposely I left off the label. That's a helpful label. your book doesn't always label things. So label it something that's helpful for you. There is one point on this graph that it would be really helpful to label. What's it look like? Yeah, that valley. That valley point would be nice to label. So give it a name. I'm going to call mine A. So I'm going to say that the x value here is the value of A, because I know that that valley point is an important point for me to reference as I'm writing down information about the graph. So just give names to the things you need names for, okay? All right, so the first thing I'm supposed to do is talk about the slope being 0. Where is my slope 0?
The y value that bottom.
Yeah. So, well, the x value. We always reference it in terms of the x value. So I called it A.
Yeah.
So whatever you called yours, that's the value you're going to write down. So the slope is 0 at, like I said, what I called A. All right, so what happens before A all the way up till we get to A? Okay, so be careful. The graph's decreasing. What's the slope? Negative. The slope is negative. As awkward as it's going to be, I'm going to say it. The slope is actually increasing. The graph is decreasing. The slope's actually increasing because it's becoming less negative as you move along. So you want to be really careful. The graph is decreasing, but we want information about the slope. The slope is negative, which is a much more helpful piece of information. What about after A, from A to infinity? Yeah, the slope is positive. Now, that's actually enough information. It's really all the information we have to be able to draw this particular graph. So we're going to draw the same thing we did before. If you called the point A, you need to call it A again. Starting at the very top, changing all my slope words to y value. The first one says my y value is 0 at A. What does that mean?
Some point on the x-axis.
Yep, I have a point on the x-axis at A. Now it says before A, the slope is negative. So what's that look like? Below the x-axis. Now here's the piece of information that they don't tell you. They don't really tell you what to draw below the x-axis, right? So there's some flexibility because this is a sketch. Depending on what this is actually an equation for will depend on what gets drawn. So it actually could look like a straight line. That's how I'm going to draw mine. But it also could look like some kind of a curve. You don't have enough information really to make a for sure statement. So if you want to draw it like that, that would be okay too. Like I said, I'm going to draw mine as a straight line for the moment.
And then the steepness of it.
You can't calculate steepness because over here on your actual first graph, there were no units.
Scale.
There's no scale. That's why. Yeah, these are really just sketches, okay? So I'm concerned about the fact that you're below the x-axis. After that, there's really not a lot I can be too concerned about. All right? What happens after the point A? Slope is positive, which means now my y value is positive, right? So where do you have y values that are positive? Above the x-axis. So whatever image you drew before should have the same kind of image after. So if you drew a straight line before, it should probably look like on the straight line on the other side. And the reason I say this is because this graph that I started with originally was symmetric, right? So whatever is going on with the slope over here has to be the same thing that's going on, but in an opposite way over here. So if you drew this, this is fine. Or let me draw one other option for you then. If you drew this over here, you'd be drawing something like that over there. Yeah.
Theoretically speaking, I mean, we have it like this.
Mm-hmm.
Could you also do it like that? So long as it's going positive and going negative.
Okay, so you're asking me if you can draw this.
Pretty much.
Okay, so can you answer his question? Is this correct? No. Why not? All right, so you're answering it from a different perspective. You're correct. But here's why it won't work, Chancellor. This piece right here is a positive y value, right? But what was I supposed to be getting?
Oh, okay.
Negative y value. So it does matter which piece is above versus which piece is below. You're always reading it left to right. So either a graph that's a line like this or that curved kind of graph would work. Okay, so this is f prime, or at least a version of what f prime could be. All right, ready to try another one? All right, this one's interesting. What is this a graph of? A line. So let's start with number 1. This is a line. Where do you get a slope of 0? You don't. The slope is never 0. So I'm just going to write that down. We don't get one. What else can you tell me about the slope? Always positive. That's a good piece of information. The slope is always positive. There is one more piece of information, and I'm going to call it like number 3 because it actually fits into that description. What did 3 say that we're sometimes going to do? Yeah. Note how the slope changes. So what can you tell me about the slope of a line?
It doesn't change.
It doesn't change. It's always the same, right? Slope has to do with steepness. The steepness never changes if you're on a line. So the slope, I'll use the phrase you guys did, never changes. Okie dokie. Change the word slopes into y value. We're going to sketch that axis. So I don't have anything to label along the x-axis, right? There were no places where I had that specific point where it said the slope's 0. So since the slope's never 0, it's never going to cross the x-axis, agreed? But it's always going to be where? Positive. It's above. So it's always going to be above the x-axis. So I need to draw something that is above the x-axis always, and the y value never changes. What's that going to look like? Horizontal line, you got it. This is a horizontal line. And again, you don't really have a height to go with for sure because you don't have any scale. So draw it just somewhere above is fine. That should look horizontal. I think it sort of does. And this is f prime. Because that's a y value that never changes, or a y value that stays constant. All right, we're going to do a couple more that... all right, so we have another graph here. This graph looks a little different than the other ones. In particular, all the other graphs that I was working with on the previous page had the ability that they could have been polynomials. This is not a polynomial graph. This is a graph of something that might be looking like e to the x, if you were to graph it. I bring that one up here at this point because I want you to know that in Calc 1, you're never going to take a derivative of e to the x. That actually doesn't happen until Calc 2. So what we're about to do in this particular graph is not something that you'll actually do with analytical means, like with formulas, until you get to next semester for those of you who do take Calc 2. All right, so this is my graph of f. The first thing we want to talk about is we want to talk about where the slope is 0.
Does it ever level off, or does it just approach it?
Well, it looks like it levels off, right, on the left. It looks like it's approaching the x-axis, agreed? But it never actually flattens completely out. You guys see that? I mean, it's got an asymptote clearly over there. So while I can say that the slope's never 0, it does look like it's nearly 0 on the left. So those are both pieces of information that would be helpful to write down. So the slope is never 0, which is true, but the slope approaches 0. And I'm going to actually use the phrase on the left, or you could say as x goes to negative infinity. This is a sketch, so I'm not too worried that our language is real precise here. We're sketching. So on the left is a good visual description anyway, so I'm going to use that phrase. What can you tell me about positive, negative stuff?
It's always positive.
It is. The slope is always positive. Very good. Now, what can you tell me if you were to draw some tangent lines in here? So I'm going to draw a couple of them in here. What can you tell me about my slope as I'm moving from left to right?
Slope is always changing.
It is changing. It's always changing. How is it changing? It's increasing. It's getting steeper, right? But again, we want to use the phrase increasing. That's a much more helpful phrase. So that's why I told you to be really careful about phrase increasing before, because you were wanting to talk about the graph increasing. And here I'm talking about slopes, right? The steepness is actually what's increasing here on my graph. So the slope is increasing. And if you want to, you can write from left to right. That gives you another visual to help with. Just to further remind yourself we are moving from left to right. Okay, what's the next thing we do after we write out all those details? You change it. Slope everywhere becomes y value. Fabulous. All right, so we're going to draw an xy axis. It's going to be roughly the same scaling, so to speak, as the one before. I need the same amount on the left and the right and so forth. So my y value is never 0, which means my graph will never do what? Never cross the x-axis. That's important to keep in mind. I will never cross the x-axis. My y value approaches 0 on the left. What does it look like for your y value to approach 0?
Like that.
It looks like that, right? It looks like as I'm moving left, if I was sort of tracing along the graph and moving left, I'm getting close to the x-axis. I drew it, although I didn't actually say it. On number 2, it says the y value is always positive, so that's why I know I'm above the x-axis, right? So I am, in fact, above the x-axis. The last thing says that I need my y value to be increasing from the left to the right. What's it going to look like?
The same thing.
Yeah. That's awful. We're going to try that again. This graph is a very unique graph. This graph is the graph of e to the x. And visually, when you have a graph of e to the x, 2 to the x, 3 to the x, 10 to the x, whatever you'd like to think about in that way, the visual image of the derivative looks exactly like the original graph. It has the same shape. None of the others do that. This is a very unique shape to do this. All right, we're going to do one tricky, and this will be our last thing we do today. So we won't get to your fun derivative rules that some of you were hoping to get to. We won't even get to number 8, I don't think. But we'll get to number 7 here. Use the graph of f to sketch the graph of f prime. So we're doing the same thing that we were on the other ones, except that this is piecewise, right? I've got lots of little pieces to talk about. All right, so let's do the same thing. We're talking about slope. What can you tell me about the slope being 0? Where is the slope 0?
3, 4, well, 3 through 5.
All right, except that at 4, it has this weird jump in it, right?
Oh, yeah.
Okay, so the slope is 0 on the interval 3 to 4 and on the interval 4 to 5. Am I in your way, Chance? Other Chance, sorry. Kind of in the way of the board there. Okay, so for 3 to 4 and for 4 to 5, the slope's 0. Agree? I've got flat pieces, so the slope is 0. All right, moving from left to right, we need to talk about, oh, you know what, let's,
Should we talk about the left side?
yeah, let's talk about the left side as well. So what's happening on the far left?
Approaching 0, but it doesn't.
Right, the slope is nearly 0 or almost 0 or approaching 0, whatever phrase you want to use, nearly 0 on the left. All right, let's move from left to right now. From negative infinity until I get to the first sort of change in the way the graph looks. That's the x-axis or the y-axis, right? What can you tell me about the slopes as I move from negative infinity to x equals 0?
They are decreasing.
But the graph is decreasing. Let's talk about positive or negative slopes first. It's negative. If I drew tangent lines along this over here, I'd get lines that look something like this, right? Those tangent lines have negative slopes. So
That's even the right term.
that is the right term, yes. The slope is negative. That's all I'm going to go with for the moment. It is negative from negative infinity to 0. What about from 0 to 3? What's going on from 0 to 3?
You have like
It's negative as well, isn't it? Look at that tangent line I just drew in. Can you see it? Because I drew it in black. That tangent line is a negative slope, right? So the slope is still negative. But it's on a different piece, so it's 0 to 3. And then we already identified what happened between 3 to 4 and 4 to 5, right? So we don't have to write down those pieces. Let's write down something, a little bit more information about these pieces that sort of are curving. The piece that's curving on the far left, we said it was a negative slope. But as I move from left to right, what can you tell me? So here's one slope line, tangent line. Here's another tangent line. What can you tell me about those tangent lines' slopes? They're steeper, right? They're steeper downhill. So one of the phrases that we could use, this is the phrase I'm going to use, is I'm going to say that the slopes, as soon as I get some space, I'm going to say that the slope is becoming more negative from left to right on the interval negative infinity to 0. As I'm moving from left to right, it is becoming more negative. Now, that's a little bit different than what's happening on the next piece. On the next piece, what is happening? Less negative, right? It's actually flattening out instead of it becoming steeper as you move from left to right. So the slope is becoming less negative from left to right on the interval 0 to 3. All right, so I need my scale to look somewhat the same. This one actually had some scale markings, so at least I need the x-axis to be scaled out. The y-axis is a little bit of a nightmare to try to think about it in that way, but I'll put in the same x-axis scaling. I need a graph that has a slope of 0 from 3 to 4 and 4 to 5. What in the world is that going to look like? On the x-axis. I'm going to be on the x-axis, and so I'm going to use the color, well, we'll use red. I was using red on the other ones. So we're going to use red, and I'm going to be on the x-axis between 3 and 4. That's probably too much. And I'm going to be on the x-axis between 4 and 5. Now, I mentioned this last time. We haven't encountered one until this problem, but anytime you have a jump on the graph, a discontinuity, that was one of those places we talked about last time is that the derivative doesn't exist. So I actually have a hole in the graph at 4 and at 3. And you could draw it either at 5 or not because we don't really know what's happening after 5. Maybe it stops, maybe it doesn't, but we can draw a hole there too. So there's holes in the graph because those places were discontinuous. All right, so that's the first piece of information I wrote down. Moving at the left, so let's do everything on the left-hand side of the y-axis. Yes?
on the 5, why did you say that you could leave that open?
I'm going to leave it open because you can't talk about a limit from both sides because it only has one side.
Okay.
So it's discontinuous after that. So there's a discontinuity there.
Okay. I was looking at the 5 as
Yeah.
okay.
All right, the left-hand side of the y-axis. Bear with me, I know we're out of time, but I want to finish the picture up real quick. It won't take us but maybe 2 more minutes, okay? On the left-hand side of the y-axis, the slope is negative, which means I am on the bottom. The slope is becoming more negative as I move from left to right, and it is nearly 0 on the far left, which means it looks the same as it already did. So this graph had that same imagery, kind of like the last example we did, as where it began. It may not be quite exactly the same graph, but it has the same basic image. The next piece, doesn't have the same image that it had before. The next piece between 0 and 3 has slopes that are negative, right? So I didn't go through and change these all, pretend like I did. These all say y value now. I need a y value that's negative. Where are y values negative? On the bottom. So this graph between 0 and 3 needs to be on the bottom. But it needs to be on the bottom, and as it moves from left to right, it's supposed to become less negative. So in a very real way, it looks like it flipped upside down. And wherever you decide to end it, it needs to have an open circle. You could say that it actually ends at the open circle that's already 3. That would be acceptable as well, because we can't really tell from the original graph. Does it really flatten out? I mean, it may. So this would be an image of the derivative graph. All right.